$10,000 quadrillion.
That's the number.
10,000 quadrillion. Let me write that out for the audience. That's a 1 followed by 19 zeros.
Which is roughly 100,000 times the entire gross domestic product of every nation on Earth combined.
And it's just floating out there between Mars and Jupiter, a potato-shaped rock the size of Massachusetts, packed with iron, nickel, gold, platinum, and enough precious metals to make every single human being on this planet a billionaire.
Theoretically.
There's always a theoretically with you, Elena.
Because theory is where the story lives and dies. We know Psyche exists. We've calculated its value. NASA has literally launched a spacecraft to go study it. But here's the cosmic joke. We can't touch it. We can't mine it. We can't bring any of that wealth back to Earth.
Why not?
That's what we're spending the next 2 hours explaining. Welcome to the $10,000 quadrillion rock we can't touch. I'm Dr. Elena Vasquez.
And I'm Marcus Chen, here to ask the uncomfortable questions about why humanity is sitting on the greatest potential treasure in the solar system and can't do a damn thing about it. We're going to talk about the Psyche asteroid, NASA's mission to reach it, the technology we don't have, the laws that don't exist, and the global space race that's heating up as we speak.
Plus, the economic paradox that would make all that wealth worthless the moment we tried to use it.
That's fun. Nothing like crushing everyone's dreams of becoming space billionaires.
That's what I'm here for.
All right, let's start with the basics. What exactly is Psyche?
16 Psyche, the 16 means it was the 16th asteroid ever discovered, is a massive M-type asteroid orbiting the Sun in the main asteroid belt between Mars and Jupiter. It was discovered on March 17, 1852, by Italian astronomer Annibale de Gasparis and named after the Greek goddess of the soul.
The goddess of the soul. That's poetic for a giant metal ball.
Well, Psyche is the Greek word for both soul and butterfly, which is why the asteroid's original symbol was a butterfly wing topped with a star. But yes, we're now talking about a 140-mile-wide chunk of metal, not ancient mythology.
140 miles. How big is that really?
It's roughly the size of Massachusetts, or if you prefer European geography, about the size of Slovenia. It's potato-shaped, most asteroids are, measuring about 173 miles long and 144 miles wide. A day on Psyche lasts just over 4 hours, while a year takes about 5 Earth years as it completes its orbit around the Sun.
And it contains 1% of the entire asteroid belt's mass?
Correct. It's one of the dozen most massive asteroids we know of, and it's definitely the largest M-type asteroid. M-type asteroids are believed to be metal-rich, which is what makes Psyche so special.
Okay, let's talk about that valuation. Where does the $10,000 quadrillion number come from?
The originated with Lindy Elkins Tanton, who's the principal investigator for NASA's Psyche mission. Back in 2017, she calculated the theoretical value of the asteroid's materials based on metal market prices at the time.
So someone actually did the math?
She did. The logic was straightforward. If Psyche is composed primarily of iron and nickel, similar to Earth's core, plus trace amounts of gold, platinum, palladium, iridium, and other precious metals found in typical metallic meteorites, what would all that material be worth on Earth's commodities markets?
And the answer was more money than has ever existed in human history?
By several orders of magnitude. The global GDP is around $100 trillion. Psyche's theoretical value is about 100,000 times that.
That's genuinely incomprehensible. My brain can't process that number.
Nobody's can. And that's actually part of the problem with how this story gets told in the media. The 10,000 quadrillion figure is technically accurate based on current market prices, but it's also essentially meaningless.
Why?
Because value isn't just about quantity, it's about supply, demand, and accessibility. We'll get into the economic paradox later, but the short version is, the moment you introduce that much material into the market, prices collapse. Those metals become nearly worthless precisely because there's so much of them.
So the 10,000 quadrillion dollar number is simultaneously true and completely fictional.
Welcome to economics and astrophysics, and basically every field that deals with extreme scales.
Okay, but let's pretend for a moment we could somehow use those resources. What's actually in Psyche that's valuable?
Based on spectroscopy and density measurements, scientists estimate Psyche is between 30 and 60% metal by volume. The primary metals would be iron and nickel. Iron accounting for about 94% of the metallic content, nickel about 5%.
That doesn't sound that exciting. Iron isn't exactly rare on Earth.
True, but here's where it gets interesting. Metallic meteorites, which are our best analog for what Psyche might contain, also include smaller amounts of cobalt, gallium, iridium, tungsten, gold, copper, rhenium, and platinum group metals.
Those trace elements are enormously valuable.
Platinum group metals, those are the ones everyone gets excited about. Right, platinum, palladium, rhodium, iridium, osmium, and ruthenium. These are critical for electronics, catalytic converters, medical devices, renewable energy technology, and industrial processes. They're rare on Earth's surface because during our planet's formation, most heavy metals sank into the core, which we can't access.
But Psyche might be an exposed planetary core.
That's the leading hypothesis. Scientists believe Psyche could be the remnant core of a protoplanet, an early planetary building block that was forming 4.5 billion years ago, but got smashed apart by violent collisions before it could fully develop.
It lost its outer rocky mantle and crust, leaving just the metallic core exposed. So we're looking at the heart of a dead planet.
Potentially. If true, studying Psyche would give us unprecedented insights into planetary formation and what our own Earth's core might look like, something we'll never be able to observe directly on our own planet.
That's actually the scientific value, isn't it? Beyond the money.
Absolutely. Even if Psyche weren't worth a single dollar, it would still be one of the most important objects to study in the solar system. We've never explored a metal-rich asteroid before. Every other asteroid we visited has been rocky or icy. Psyche is completely unique.
But here's my skeptical journalist question. How do we actually know what Psyche is made of? We've never been there. No spacecraft has collected samples. Aren't we just guessing?
We're making educated inferences from multiple lines of evidence. First, spectroscopy. Analyzing the light reflected from Psyche's surface tells us about its composition. Metal-rich surfaces reflect light differently than rocky ones. Second, radar observations. Psyche's radar albedo, how it reflects radio waves, is 2 to 4 times higher than most main belt asteroids, consistent with metallic surfaces.
And third?
And third, density. Based on its gravitational effects and size, we've estimated Psyche's density at around 3.4 to 4.1 grams per cubic centimeter. That's denser than most rocky asteroids, but actually less dense than pure iron-nickel.
Wait, less dense than pure metal? Does that mean it's not as metallic as we thought?
This is where the story gets complicated. If Psyche were a solid chunk of iron-nickel, its density should be around 7 to 8 grams per cubic centimeter. The lower measured density suggests one of two things. Either Psyche contains significant amounts of rock mixed with the metal, or it's porous, full of empty spaces and cracks.
Like a metal sponge.
Exactly. Recent studies have suggested Psyche might be more like a rubble pile than a solid core, a collection of fragments loosely held together by gravity rather than an intact planetary heart.
That sounds like a significant downgrade from the core of a dead planet.
It's more nuanced. A 2021 study from the University of Arizona suggested Psyche might be only 82.5% metal with about 7% rock-forming minerals and 10.5% carbonaceous chondrite material on its surface.
So still mostly metal, but not the pure iron-nickel some people imagined.
Right. And this actually makes sense from a formation perspective. If Psyche was exposed to billions of years of asteroid impacts, it would have accumulated debris from other space rocks, creating a mixed surface layer.
How does this affect the $10,000 quadrillion valuation?
It reduces it somewhat, but we're still talking about incomprehensible amounts of metal. Even at 30% metal content, Psyche contains more iron and nickel than humanity has ever extracted from Earth in all of history.
So the treasure is real, just maybe not quite as shiny as the headlines suggest.
The treasure is real. Getting to it is the fantasy.
All right, let's talk about the most recent wrinkle in this story. You mentioned something to me before we started recording about rust?
Yes, the rust situation. In August 2024, scientists using the James Webb Telescope confirmed the presence of hydroxyl signatures on Psyche's surface.
Hydroxyl. That's water-related.
Hydroxyls are oxygen-hydrogen molecules. When they bond with metals, they can form oxidation, essentially rust. The findings suggest that Psyche's surface metals may have been reacting with water-bearing asteroids that collided with it over billions of years.
So the $10,000 quadrillion rock is covered in rust?
Potentially, yes, though covered might be an overstatement. We don't know the extent or depth of the oxidation, but it adds another layer of complexity to understanding what we'd actually find if we ever landed on Psyche.
This is like finding out the sunken treasure ship is full of corroded coins.
A reasonable analogy, though the underlying metals would still be there, just requiring additional processing.
Okay, I want to step back and ask the obvious question that nobody seems to address. Why does this asteroid even exist? How do you end up with a giant metal ball floating in space?
Great question. There are two main theories. The first, and most exciting, is the exposed core hypothesis. During the early solar system, around 4.5 billion years ago, countless protoplanets were forming. These were rocky bodies large enough to differentiate, meaning their interiors separated into layers, with heavy metals sinking to form cores and lighter materials forming mantles and crusts.
Like Earth has a core, mantle, and crust.
Exactly. The theory suggests that one of these protoplanets got pummeled by catastrophic collisions that stripped away its outer layers, leaving just the metallic core exposed. That naked core is what we now call Psyche.
What's the other theory?
That Psyche isn't an exposed core at all, but rather primordial material, metal-rich stuff that never fully melted and differentiated in the first place. Some regions of the early solar system may have had higher concentrations of metallic grains that clumped together without undergoing planetary scale melting.
So either a destroyed planet's heart or just weird primordial leftovers.
Right. And distinguishing between these scenarios is actually one of the primary science goals of NASA's Psyche mission. If it's an exposed core, we'll learn about planetary differentiation and core formation. If it's primordial material, we'll learn about the raw ingredients that built the planets.
Either way, we learn something fundamental about how our solar system formed.
Exactly. The scientific value is immense, regardless of which hypothesis is correct.
Let's talk about location. Where exactly is this thing?
Psyche orbits in the main asteroid belt, approximately 235 to 309 million miles from the Sun, or about 2.5 to 3.3 astronomical units. An astronomical unit is the distance from Earth to the Sun, roughly 93 million miles.
So it's way out there.
Very much so. For comparison, Mars is about 1.5 AU from the Sun at its closest. Psyche is more than twice as far. At its closest approach to Earth, it's about 186 million miles away. At its farthest, over 370 million miles.
That distance is part of why we can't just go grab it, I assume.
It's a major factor. Distance equals time, fuel, and complexity, but we'll get into the technological challenges later. For now, just understand that Psyche isn't a convenient rock parked next to Earth. It's deep in the asteroid belt, following its own orbital path that only sometimes brings it relatively close to us.
Define relatively close.
At opposition, when Earth passes between Psyche and the Sun, it can be about 1.7 AU away, which is still about 160 million miles. That's roughly the distance to Mars, but Psyche's orbit means we can't just launch whenever we want. The orbital mechanics have to align.
And that's why the NASA mission took so long to plan.
Partly, there's a narrow window of opportunity for launch that occurs roughly every 5 years, based on Earth's and Psyche's positions. Miss it, and you wait years for the next chance.
All right, I think we've established what Psyche is and where it lives. We need to talk about what NASA is actually doing about this cosmic treasure chest.
We've established that there's a 10,000 quadrillion dollar asteroid floating between Mars and Jupiter, and now we need to talk about the spacecraft NASA sent to investigate it. Elena, give us the basics.
NASA's Psyche mission launched on October 13, 2023, from Kennedy Space Center in Florida aboard a SpaceX Falcon Heavy rocket. It's currently en route to the asteroid and will arrive in August 2029, after a journey of about 2.2 billion miles.
6 years to get there?
Nearly 6 years, yes. The spacecraft will spend at least 26 months orbiting the asteroid, conducting detailed observations from various altitudes. The total mission is expected to end around November 2031.
And this was a troubled development, right? I seem to remember headlines about delays.
Oh, it was quite the saga. Originally, Psyche was supposed to launch in 2022 with a more efficient trajectory that would have reached the asteroid by 2026. But the mission hit serious problems with its flight software and testing schedule.
What happened?
An independent review in November 2022 found understaffing at the Jet Propulsion Laboratory, insufficient planning, and communication breakdowns between engineers and management. The software issues were significant enough that NASA had to delay the entire mission by a year.
That's a big deal for a deep space mission.
Massive. The delay even affected another mission, Veritas, a planned Venus mission, which got postponed to free up staff and resources for Psyche. There were real questions about whether Psyche would ever launch.
But it did launch eventually.
October 13, 2023. And the launch itself was actually delayed by a few days. First, due to last-minute spacecraft checks, then due to weather. But it finally got off the ground, and by all accounts, the spacecraft is performing well.
What's the current status?
As of late 2025, Psyche is cruising through space and on track for its Mars gravity assist in May 2026. That maneuver will use Mars's gravity to slingshot the spacecraft toward the outer asteroid belt. There was a brief hiccup in April 2025 when engineers detected a pressure drop in the propulsion system's fuel line, but they successfully switched to a backup line and resumed full thruster operations in June.
So the spacecraft is healthy?
Healthy and on schedule. It's been firing its Hall effect thrusters. These are super efficient electric propulsion systems to gradually adjust its trajectory. The thrusters use ionized xenon gas, which provides incredible fuel efficiency compared to traditional chemical rockets.
Hall effect thrusters. That sounds very sci-fi.
They're actually proven technology, but this is the first interplanetary mission to use them as the primary propulsion system. Hall effect thrusters produce much less thrust than chemical engines. Imagine the force of holding 3 quarters in your palm, but they can operate continuously for months or years, slowly building up tremendous velocity.
So it's the tortoise versus the hare approach?
Perfect analogy. Chemical rockets are hares, explosive bursts of speed that quickly exhaust their fuel. Electric propulsion is the tortoise, slow and steady, but ultimately winning the race for fuel efficiency.
What's the spacecraft actually carrying? What instruments will study Psyche?
There are 4 main science instruments. First, a multispectral imager, essentially a high-resolution camera with multiple filters that can capture images in different wavelengths of light. This will map Psyche's surface in incredible detail.
Looking for what?
Composition variations across the surface. Different minerals and metals reflect light differently, so multispectral imaging can reveal where metal concentrations are higher or lower, where there might be silicate rocks, and what the overall terrain looks like.
Instrument 2?
A gamma ray and neutron spectrometer, the GRNS.
This detects gamma rays and neutrons emitted from Psyche's surface when it's bombarded by cosmic rays. Different elements produce distinctive radiation signatures, so this instrument can determine what elements are present and in what proportions.
Cosmic rays as a natural X-ray machine?
Essentially, yes. Third, a magnetometer. This will measure any remnant magnetic field around Psyche. If it was once the core of a protoplanet, it might still retain traces of magnetism from when that core was molten and generating a magnetic dynamo, similar to how Earth's liquid core creates our magnetic field.
And if it's not a former core?
Then we'd expect little to no magnetic signature. The magnetometer results will be crucial for determining Psyche's origin story.
What's the fourth instrument?
The X-band radio telecommunications system, which isn't really a science instrument in the traditional sense, but scientists will use it to study Psyche's gravity field. By precisely tracking how the spacecraft's radio signals are affected as it orbits the asteroid, we can map the internal mass distribution and determine whether Psyche has a dense core, is uniformly structured, or is actually porous and fragmented.
So the spacecraft's radio becomes a gravity detector.
Exactly. The technique is called radio science, and it's been used successfully on many planetary missions.
There's also something else on this spacecraft, right? Some kind of technology demonstration?
Yes, the Deep Space Optical Communications Experiment, the DSOC. This is a laser communication system that NASA is testing for future missions. Instead of traditional radio waves, DSOC uses near-infrared laser light to transmit data back to Earth.
Lasers for deep space communication? That sounds very next generation.
It is. The potential advantages are enormous. Laser communications can transmit data at much higher rates than radio. We're talking 10 to 100 times faster. During tests in December 2023, DSOC transmitted data at up to 267 megabits per second from 31 million kilometers away. That's comparable to broadband internet speeds.
Wait, they beamed internet speed data from deep space?
They literally sent a cat video, an engineer's cat playing with a laser pointer, no less.
Of course, the first thing we transmit at unprecedented deep space data rates is a cat video. Humanity is consistent, if nothing else.
The internet transcends all boundaries, apparently. But seriously, DSOC is a game changer for future missions. Higher data rates mean we can send more science data, higher resolution images, and eventually video from deep space. It's critical infrastructure for human exploration of Mars and beyond.
All right, let's talk about the mission profile once Psyche arrives at the asteroid. What's the plan?
The spacecraft will approach Psyche starting around May 2029, taking about 100 days to carefully maneuver into orbit. During this approach phase, the imager will provide increasingly detailed views for both navigation and early science.
And then it starts orbiting?
Yes, in a carefully planned sequence of orbits at different altitudes. NASA has designated them Orbit A through D, but they won't be visited in that order. The sequence is A, B1, D, C, and finally B2.
That's confusing. Why not just A, B, C, D?
It's driven by the changing amount of sunlight reaching Psyche as it orbits the Sun. Different observations require different lighting conditions. Orbit A is the highest at about 440 miles above the surface. Orbit D is the lowest at just 47 miles above the surface.
47 miles above the surface of an asteroid worth $10,000 quadrillion. That's close enough to almost taste the metal.
I wouldn't recommend tasting it, but yes, that's incredibly close. At that altitude, the instruments can capture extraordinarily detailed data about surface composition and structure.
Will the spacecraft land?
No, this is strictly an orbital mission. No landing, no sample collection, no physical contact with the asteroid. The spacecraft will remain in orbit, gathering data remotely.
That's frustrating. We're sending a billion-dollar spacecraft all that way, and we're not going to touch it?
The mission cost is actually about $1.2 billion, including the launch. And yes, it's observation only, but that's by design. This is a reconnaissance mission, the first step in understanding Psyche before any future missions could attempt anything more ambitious.
Like mining missions.
Theoretically, yes, though as we'll discuss, mining Psyche specifically is probably not realistic for a very, very long time.
We'll get to that. But first, I want to address something. The mission is called Psyche, the asteroid is called Psyche, and the spacecraft is called Psyche. Who thought this was a good idea?
Like it's NASA tradition, actually. The Dawn mission went to Vesta and Ceres, OSIRIS-REx went to Bennu, and Psyche goes to Psyche. It can get confusing in conversation, I admit.
Okay, so let's be clear. Psyche the spacecraft is currently traveling towards Psyche the asteroid to complete the Psyche mission.
Correct on all counts.
This is why people think scientists are bad at naming things.
Fair criticism.
Let's talk about what we hope to learn. What are the big science questions this mission is trying to answer?
There are 5 primary science objectives. First, determine whether Psyche is actually a core or if it's unmelted primordial material. Second, determine the relative ages of different regions on the asteroid's surface. Which parts are older, which are younger.
How do you age an asteroid surface?
Crater counting primarily. Older surfaces have accumulated more impact craters. Younger surfaces, created by geological activity or major impacts, have fewer craters. It's not precise, but it gives relative ages.
Objectives 3, 4, and 5?
3. Determine whether the metallic regions differ in iron and nickel content from what we see in iron meteorites on Earth. 4. Determine whether Psyche formed under more oxidizing or more reducing conditions than Earth's core. And 5. Characterize Psyche's topography. Map its mountains, craters, ridges, and other surface features.
That last one seems more straightforward.
It is, but the results will feed into answering the bigger questions. Topography tells us about geological processes. Did this surface form through volcanic activity, impacts, cooling and contraction? The shape tells a story.
What are scientists most excited about?
I think the biggest excitement is around the exposed core hypothesis. If we can confirm that Psyche is the remnant core of a protoplanet, we'll have the opportunity to study something we could never study on Earth, what a planetary core actually looks like. Earth's core is 1,800 miles beneath our feet, beyond any possible direct observation. Psyche could be that core, exposed to view.
And if it's not a core, if it's just primordial rubble,
Then we learn something equally fascinating about the diversity of asteroid compositions and the building blocks of planets. Either way, we win scientifically.
but the media won't care as much about primordial rubble.
Probably not. Ancient space junk worth trillions doesn't have the same ring as heart of a dead planet.
All right, we also need to tackle the elephant in the room. If this asteroid is worth 10,000 quadrillion, why the hell can't we go get it?
We've been dancing around this question, and now it's time to confront it directly. The Psyche asteroid is theoretically worth more than all the money ever created in human history. Why can't we mine it?
Because every single technology we would need to do so either doesn't exist yet or isn't reliable enough for commercial scale operations in deep space.
Walk me through the challenges. What would we actually need?
Let's break it down step by step. First, you need to get to Psyche. That means spacecraft capable of reaching the asteroid belt, which requires either chemical propulsion with massive fuel loads or advanced electric propulsion systems like the ones on NASA's Psyche spacecraft.
We can do that. We literally just launched a spacecraft to Psyche.
We can send a small observation spacecraft, yes, but mining operations would require massive infrastructure, excavation equipment, processing facilities, storage containers, power generation systems. The mass requirements are completely different.
How different?
NASA's Psyche spacecraft weighs about 6,000 pounds fully fueled. A realistic mining operation would need equipment weighing tens of thousands or hundreds of thousands of pounds. That's not something we can launch with current technology, at least not economically.
What about Starship's Starship? That's supposed to be able to lift over 100 tons to orbit.
Starship is promising, and if it becomes fully operational and reliable, it could change the equation. But even then, launching heavy equipment to low Earth orbit is just the first step. You still need to get it from Earth orbit to the asteroid belt, a journey of years, and then operate it in one of the most hostile environments imaginable.
Let's talk about that environment. What's it like on Psyche's surface?
First, there's almost no gravity. Psyche's surface gravity is about 0.5% of Earth's. If you jumped, you'd float away into space. Any mining equipment would need to anchor itself to the surface, and any excavated material would drift away unless contained.
So you can't just dig a hole.
You can't dig in any conventional sense. There's no weight to press machinery into the ground, no friction to grip, no atmosphere to contain dust. Every assumption from terrestrial mining breaks down.
What else?
Extreme temperature variations. On the asteroid surface, temperatures can swing from around -225 degrees Celsius in shadow to perhaps 100 degrees Celsius or higher in direct sunlight. Equipment would need to survive repeated thermal cycling over years of operation.
And communication delays?
Significant. At Psyche's distance, signals take anywhere from 10 to 30 minutes to reach Earth, depending on orbital positions. Real-time control is impossible. Any mining operation would need to be largely autonomous, capable of making complex decisions without human input.
That's a tall order for excavation equipment.
Extremely tall. We have some autonomous mining technology on Earth, but nothing that can operate reliably for years without maintenance in a microgravity vacuum environment millions of miles from any repair crew.
Let's say we somehow figure out the extraction. How do we process the ore?
That's the next massive challenge. On Earth, ore processing typically involves crushing, heating, chemical treatments, and refining, processes that rely on gravity, convection, and controlled atmospheric conditions. None of those exist in space.
Astroforge, one of the asteroid mining startups, has been testing space-based refining technology. What's their approach?
Astroforge plans to use a technique similar to laser ablation, vaporizing metal from asteroid material and then using magnetic fields to separate the vaporized metals from other constituents. It's clever, but it's never been demonstrated at scale on actual asteroid material.
They launched a test mission in 2023, right?
They did. Brocker 1, a small CubeSat carrying asteroid-like simulant and a prototype refinery. Unfortunately, they had communication problems and couldn't fully execute the demonstration. Their second mission, Odin, launched in February 2025 and was intended to fly by a near-Earth asteroid, but they lost contact with the spacecraft.
So the most advanced private asteroid mining company has already had 2 missions encounter serious problems?
Space is hard, really hard, and these are pioneering efforts. They're learning lessons that will inform future attempts, but it illustrates how far we are from routine commercial operations.
What about bringing material back to Earth? Even if we could mine and process it, how do we get it home?
This is arguably the biggest engineering challenge of all. Any return mission from the asteroid belt would take years. The material would need to be packaged, protected, and guided on a precise trajectory back to Earth. Then it would need to survive atmospheric re-entry, which generates tremendous heat, and land safely with its cargo intact.
NASA brought back asteroid samples from Bennu. That worked.
OSIRIS-REx brought back about 250 grams of material from a near-Earth asteroid, roughly half a pound. That's an incredible achievement, but it's fundamentally different from the hundreds or thousands of tons a commercial mining operation would need to return to be economically viable.
So we're talking about scaling by a factor of what?
Millions, maybe tens of millions. The gap between current sample return capabilities and commercial-scale asteroid mining is roughly equivalent to the gap between the Wright brothers' first flight and the Boeing 747.
How long did that take? About 60 years?
About that, yes. And aerospace developed with massive government investment, wartime urgency, and commercial airline demand. Space mining doesn't have equivalent drivers, yet.
What do the experts estimate for timeline?
Ian Lang at the Colorado School of Mines, one of the leading authorities on space mining economics, estimates that full-scale commercial asteroid mining is probably 30 years away. Initial technology demonstrations will happen this decade, but economically viable extraction at meaningful scale, 2050s or later.
So we're not going to see asteroid billionaires in our lifetime?
I wouldn't say never, but probably not from asteroid belt objects like Psyche. Near-Earth asteroids are more realistic early targets. Shorter travel times, lower delta-V requirements, more frequent launch windows.
Delta V?
The change in velocity required to reach a destination. It's the fundamental currency of space travel. Getting to Psyche requires much higher delta-V than reaching a nearby asteroid that happens to pass close to Earth.
So even within asteroid mining, Psyche isn't the low-hanging fruit.
Psyche is very high-hanging fruit, spectacularly valuable if we could reach it, but realistically, commercial interest will focus on near-Earth asteroids first. Those are orders of magnitude easier to access.
What about in-space utilization versus bringing resources back to Earth?
That's actually a more promising near-term model. Several companies, Transastra, Carmen Plus, are focused on extracting water and volatiles from asteroids to produce rocket propellant in space. Water can be split into hydrogen and oxygen, which are rocket fuels.
Space gas stations.
Exactly. If you could refuel spacecraft in orbit or at strategic points throughout the solar system, it would dramatically reduce launch costs and enable more ambitious missions. You'd never need to lift all that fuel from Earth's surface.
But that still requires solving all the same technological challenges: extraction, processing, storage, and space.
It does, but the economics are more favorable. You're not trying to compete with terrestrial mining prices. You're providing a service that literally cannot be obtained any other way. There's no alternative to in-space propellant manufacturing except launching more fuel from Earth, which is enormously expensive.
What's the current state of the market? How much money is flowing into space mining?
The space mining market was valued at about $2 billion in 2024, and projections suggest it could reach $18 billion by 2034. That's mostly investment in developing technologies, not actual mining revenue, because no one has mined anything.
$2 billion sounds like a lot, but in context,
It's tiny compared to terrestrial mining, which is a multi-trillion-dollar industry. Space mining is still in the research and development phase, not commercial production.
let's talk about the companies. Who are the serious players?
Astroforge is the most publicly visible, founded in 2022 with plans to extract platinum group metals. They've raised over $55 million and are working on their third mission, Vestry, which aims to land on a metallic near-Earth asteroid.
After losing their second spacecraft?
After losing their second spacecraft, yes. But they're iterating quickly and learning from failures. That's how aerospace development works.
Who else?
Transastra, founded by former NASA engineer Joel Searle, is developing optical mining technology, using concentrated sunlight to heat asteroids and release volatile materials. They're also building telescope systems to identify promising targets. Carmen Plus has raised $20 million with plans for a 2027 mission to demonstrate water extraction. And there are international players. Origin Space in China has an asteroid-observing satellite in orbit and is testing relevant technologies.
I noticed you mentioned China. We should probably talk about the space race angle later.
Definitely. It's a significant factor.
Before we move on, I want to address something. Why did the earlier asteroid mining companies fail? Planetary Resources and Deep Space Industries had real investment, real engineers, real plans. What happened?
Money ran out. Both companies were founded in the early 2010s with ambitious timelines that proved unrealistic. Investors got tired of funding projects that were always 10 years away from any return. Planetary Resources was acquired by Consensus, a blockchain company, and pivoted away from asteroid mining. Deep Space Industries was acquired by Bradford Space and redirected to other endeavors.
So the first wave of asteroid mining companies basically evaporated.
Without ever reaching an asteroid. The current generation of companies, Astroforge, Transastra, Carmen Plus, are trying to learn from those failures by developing revenue streams from terrestrial applications while pursuing their space ambitions.
Like what?
Asteroid Mining Corporation in the UK is developing a six-legged robot called SCAR-E that can operate in microgravity. But instead of waiting until they can send it to space, they're commercializing it for ship hull inspections on Earth, a real market that generates immediate revenue.
Clever. Don't wait for the space economy to fund the space economy.
Exactly. Bootstrap with existing markets, then transition to space when the technology and economics align.
All right, we need to tackle the legal quagmire because apparently, even if we could mine Psyche, nobody's sure if that's legal.
We've established that mining Psyche is technologically impossible right now. But let's imagine we somehow solve all those problems. Can we actually own what we mine? What are the legal frameworks?
This is where things get genuinely murky. The foundational document for international space law is the 1967 Outer Space Treaty, which was negotiated during the Cold War primarily as an arms control agreement.
What does it say about resources?
Here's Article 2. Outer space, including the moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means.
That sounds like a pretty clear no to claiming asteroids.
It's clear about nations not claiming sovereignty over celestial bodies. What's less clear is whether that prohibition extends to extracting resources for private profit. The treaty was written in 1967. Nobody was seriously thinking about asteroid mining.
So there's a gap in the law.
A significant gap. The key question is, does mining resources from an asteroid constitute national appropriation? Or is it more like fishing in international waters where you can extract and sell resources without claiming ownership of the ocean itself?
What's the U.S. position?
In 2015, the United States passed the Commercial Space Launch Competitiveness Act, sometimes called the Space Act. It explicitly grants U.S. citizens the right to engage in commercial exploitation of space resources, including water and minerals from asteroids.
So America said, we're going to mine asteroids. International law be damned.
Not quite. The law explicitly states that the United States does not thereby assert sovereignty or sovereign or exclusive rights or jurisdiction over or the ownership of any celestial body. The legal theory is that you can own resources you extract without claiming the asteroid itself, the fishing analogy.
Does the international community buy that?
It's contested. Some scholars argue that extracting resources is inherently an act of appropriation and violates the spirit of the Outer Space Treaty. Others argue that the treaty only prohibits national territorial claims, not commercial resource extraction by private entities.
Who has signed on to the U.S. interpretation?
Several countries have passed similar laws. Luxembourg enacted a space resources law in 2017, specifically to attract space mining companies to establish operations there. Japan passed a Space Resources Act. The UAE has similar legislation.
So there's a growing coalition of space mining is legal countries.
There is. And then there are the Artemis Accords, launched by NASA in 2020, which are bilateral agreements between the U.S. and partner nations establishing principles for lunar exploration and eventually broader space activity.
What do the Artemis Accords say about resources?
Section 10 affirms that the extraction of space resources does not inherently constitute national appropriation under Article 2 of the Outer Space Treaty. It explicitly endorses the idea that you can extract and use space resources in compliance with the treaty.
How many countries have signed the Artemis Accords?
Over 43 as of late 2025, including major space powers like Japan, the UK, Canada, Australia, and several European nations.
Who hasn't signed?
Russia and China, notably. They've voiced objections to what they see as American attempts to unilaterally define space law. There's a real geopolitical divide emerging, a U.S.-led bloc that supports commercial space resource extraction, and a potential China-Russia bloc that may advocate for more restrictive, internationally controlled approaches.
What about the Moon Treaty?
The Moon Treaty. That's the 1979 agreement governing the activities of states on the moon and other celestial bodies.
It explicitly declares lunar resources to be the common heritage of mankind and calls for an international regime to govern resource exploitation.
That sounds like it would prohibit space mining.
It would heavily restrict it, yes. But here's the thing. Almost no major spacefaring nation has ratified the Moon Treaty. The US, Russia, China, Japan, India, none of them signed. Only 18 countries are parties to it, and none have significant space programs.
So the treaty that actually addresses space resources is essentially letter law.
Effectively, yes. The major players ignored it, which means the more ambiguous Outer Space Treaty remains the primary legal framework.
Let me play devil's advocate here. Why does any of this matter? If the US wants to mine asteroids and has the technology to do it, who's going to stop them?
That's the realpolitik question. And in practical terms, you're right. If a country or company has the capability to extract space resources, enforcement of opposing legal interpretations would be difficult. There's no space police.
So it's essentially a free-for-all for whoever gets there first?
Right now, yes, but that creates long-term risks. If nations act unilaterally without agreed-upon rules, it could lead to conflicts, competing claims, interference with each other's operations, even sabotage. We saw hints of this with concerns about satellite constellations and orbital debris.
What about safety zones? I've heard that term thrown around.
The Artemis Accords introduced the concept of safety zones around mining operations, areas where other actors shouldn't operate to avoid interference. But it's voluntary coordination, not enforceable law.
Is there any movement toward creating real international space mining law?
There's discussion at the United Nations Committee on the Peaceful Uses of Outer Space, COPIUS, but progress is slow. The fundamental disagreement is whether space resources should be governed by a common heritage principle with international oversight and benefit sharing, or a more market-oriented approach, where whoever mines it keeps it.
Which approach is winning?
The market-oriented approach, by practice, if not by consensus. As more countries pass domestic laws permitting space mining, it becomes harder to argue that such activities are inherently illegal. Customary international law develops through state practice, and the practice is increasingly pointing toward permitted extraction.
Let's talk about practical scenarios. Say Astroforge successfully mines platinum from an asteroid and brings it back to Earth. What happens legally?
Under U.S. law, Astroforge would own that platinum. They could sell it on the commodities market like any other mined resource. The Commercial Space Launch Competitiveness Act grants them explicit property rights over extracted materials.
Would any country contest that?
Countries like Russia or China might issue diplomatic objections, but they probably wouldn't take concrete action. The practical reality is that challenging ownership of asteroid-mined resources would require some enforcement mechanism that doesn't exist.
What if China mines an asteroid? Are they following the same logic?
China hasn't passed equivalent explicit legislation, but they're pursuing asteroid sample return missions. Tianwen-2, launching in 2025, will collect samples from a near-Earth asteroid. In practice, they're asserting the same right to use space resources.
So everyone's doing it while arguing about whether it's legal.
Welcome to international law. The gap between stated principles and practical behavior is often enormous.
What happens if two entities, countries or companies, want to mine the same asteroid?
That's an unresolved question. There's no first-come, first-served registration system for asteroid claims. The Artemis Accords suggest coordination and safety zones, but they don't address exclusive mining rights.
So we could theoretically have competing operations on the same space rock.
Theoretically, yes. In practice, asteroids are numerous, over 1.3 million cataloged, and the technology is so nascent that competition for specific bodies is probably decades away. By then, hopefully clearer rules will exist.
Let's talk about liability. If a space mining operation goes wrong, debris damages another spacecraft, a processing accident pollutes the space environment, who's responsible?
Under the Outer Space Treaty and the 1972 Liability Convention, the launching state bears international responsibility for damage caused by its space objects.
So if an American company's mining spacecraft causes damage, the U.S. government is liable.
Not the company?
The company might face domestic liability under various laws, but internationally, it's state responsibility. This creates interesting dynamics. Governments have incentive to regulate their private space actors to avoid liability exposure.
Has this ever been tested?
Not for mining operations, since none exist yet. But the liability convention was invoked once after the Soviet satellite Cosmos 954 crashed in Canada in 1978, spreading radioactive debris. The Soviet Union eventually paid Canada $3 million in settlement.
That seems low.
It was negotiated down significantly from Canada's initial claims, but it established precedent that the convention can work. One more legal question. If we ever do mine Psyche or any asteroid worth trillions, would the value be taxable? Who gets to tax space wealth? That depends on where the company is incorporated, where it sells the resources, and applicable tax treaties. A U.S. company would presumably pay U.S. taxes on profits, but there's no space tax that goes to the international community, despite arguments that space resources should benefit all humanity.
So a company could theoretically extract trillions of dollars of value from the common heritage of mankind and keep all the profits.
Under current legal frameworks, essentially, yes. That's one of the criticisms. The Outer Space Treaty declares space the province of all mankind, but there's no mechanism to translate that into shared benefits.
This feels like the kind of thing that will cause enormous controversy eventually.
Almost certainly, but eventually is doing a lot of work in that sentence. Until space mining becomes economically significant, the debates remain largely theoretical.
And now we're going to zoom out from individual companies and look at the bigger picture. Elena, we're in the middle of a new space race, aren't we?
Absolutely. And unlike the original space race between the US and Soviet Union, which was primarily about prestige and military capability, this one has strong economic dimensions. Control of space resources could define which nations lead the economy of the 22nd century.
Who are the main players?
The United States remains the most advanced overall, but China is closing the gap rapidly. Russia has legacy capabilities but limited funding. Japan, India, and the European Space Agency are also significant players. And increasingly, private companies are becoming actors in their own right.
Let's start with China. What are they doing in space resources?
China has been remarkably ambitious. Their Tianwen-2 mission, launching in 2025, will collect samples from a near-Earth asteroid called 2016 HO3, also known as Kamoa-Lea, and return them to Earth by 2027.
That's an asteroid sample return mission?
Yes, similar to Japan's Hayabusa missions and NASA's OSIRIS-REx, but China is now joining that exclusive club. And they're not stopping there. They've announced plans for a flying robot to search for water ice on the far side of the moon, crewed lunar landings by 2030, and potentially a lunar research base.
And there's Origin Space?
Origin Space is a Chinese private company working on asteroid mining technology. They already have an asteroid observing satellite in orbit and are developing mining-relevant systems. The Chinese government has been clear that they view space resources as strategically important.
Has China signed the Artemis Accords?
No. And there are legal restrictions. The Wolf Amendment prohibits NASA from cooperating with China without congressional approval. This has created two emerging blocs in space governance: the Artemis Accords nations, led by the U.S., and a potential China-Russia alignment with a different vision.
What's Russia doing?
Russia's space program has struggled with funding since the Soviet era's peak, but they still have significant capabilities. They've partnered with China on lunar exploration plans and share opposition to the U.S.-led approach to space resources. However, Russia isn't in a position to lead a space mining effort independently.
What about the strategic implications? Why does any of this matter beyond economic value?
3 reasons. First, whoever controls in-space refueling infrastructure controls access to the outer solar system. If American companies provide the fuel depots, American spacecraft have advantages. If Chinese infrastructure dominates, the calculus shifts.
Space as a choke point.
Exactly. Second, space resources could reduce dependence on terrestrial supply chains for critical minerals. If you can source platinum, cobalt, rare earth elements from asteroids, you're less vulnerable to geopolitical disruptions on Earth.
Like China's dominance of rare earth mining.
That's a perfect example. About 60% of rare earth elements are mined in China, and they've used that leverage politically. Space mining could eventually break that monopoly or create new dependencies depending on who dominates the technology.
And the third reason?
Military implications. Space has always had security dimensions, but resource extraction adds new layers. Mining operations require protecting, both the spacecraft themselves and the data about valuable deposits. We're already seeing concerns about anti-satellite weapons, space domain awareness, and the militarization of cislunar space.
Cislunar?
The region between Earth and the Moon, increasingly a zone of strategic interest as lunar activities intensify.
Let's talk about the Moon for a moment. That's closer than the asteroid belt. Is that where the near-term action is?
Very much so. Lunar resources, particularly water ice at the poles, are the most accessible space resources. Multiple nations and companies are racing to explore and eventually exploit lunar ice for rocket propellant and life support.
Who's ahead?
NASA's Artemis program aims to return humans to the Moon and establish sustainable presence by the late 2020s. China plans crewed lunar landings by 2030 and a lunar base shortly after. India's Chandrayaan program has been exploring the Moon, and several private companies, Astrobotic, Intuitive Machines, iSpace, are developing lunar landers.
Australia is getting involved too, right?
Yes, Australia is planning a 2026 lunar rover mission that will test oxygen extraction from lunar soil, leveraging their expertise in terrestrial mining for space applications.
It seems like the Moon is the stepping stone and asteroids are the longer-term goal.
That's a reasonable way to think about it. Lunar activities develop the technologies, in situ resource utilization, autonomous mining, propellant production, that will eventually enable asteroid mining. Each step funds and informs the next.
Let's come back to Psyche specifically. Given all these dynamics, what role does NASA's Psyche mission play?
Psyche is fundamentally a science mission, not a precursor to mining, but the knowledge it generates will inform future planning. Understanding what metal-rich asteroids are actually made of, their composition, structure, accessibility, is essential for evaluating mining prospects.
So even though we're not mining Psyche, studying it helps future mining efforts.
Precisely. Every deep space mission adds to our understanding of what's out there and how to operate in those environments.
What about the technology demonstrations? You mentioned DSOC and the electric propulsion system.
Those have direct applications for future resource missions. High-bandwidth laser communications would allow mining operations to send detailed data back to Earth. Efficient electric propulsion reduces fuel requirements for reaching distant targets. Each technology tested on Psyche is a building block.
I want to ask about the Artemis Accords again. You said over 43 nations have signed. What does that actually commit them to?
The accords are non-binding. They're political commitments, not legal obligations. But they establish shared principles: peaceful purposes, transparency, interoperability, emergency assistance, registration of space objects, release of scientific data, protection of heritage sites, and the approach to space resources we discussed.
Non-binding seems weak.
It is, deliberately. The U.S. wanted broad participation, and legally binding treaties are much harder to negotiate. The strategy is to build consensus through accumulating signatories, creating norms through practice rather than formal law.
Is it working?
It's gaining momentum. Each new signatory adds legitimacy, but the key players who haven't signed, China and Russia, represent a significant alternative pole. We could end up with a fragmented space governance environment rather than unified rules.
What would that mean practically?
Potential for conflict. If American and Chinese mining operations end up targeting the same resources with different legal frameworks, there's no mechanism to resolve disputes. We'd essentially be relying on great power restraint rather than rule of law.
That's not reassuring.
Space governance is a work in progress. We're in a period analogous to the early days of maritime law, practices developing faster than rules, with conflicts likely before consensus emerges.
Let's talk about planetary defense. You mentioned earlier that asteroid research has implications beyond mining.
Yes, there's a dual-use nature to asteroid technology. The same capabilities that enable mining, detecting, tracking, reaching, and manipulating asteroids are also what you need for planetary defense.
Protecting Earth from asteroid impacts.
Exactly. NASA's DART mission demonstrated that we can deflect an asteroid by hitting it with a spacecraft. The ESA's Hera mission, arriving at the Didymus system in 2026, will study the results in detail. China has announced plans for asteroid deflection tests as well.
So asteroid mining and planetary defense are essentially the same skill set?
Largely, yes. If you can rendezvous with an asteroid, land on it, and alter its trajectory or composition for mining purposes, you can do the same for defense purposes. There's a national security dimension to space mining capabilities that goes beyond economics.
Is that driving government investment?
It's certainly a factor. Governments are more willing to fund technologies that have dual-use applications. Planetary defense is uncontroversially beneficial, which provides political cover for programs that also advance resource capabilities.
Before we move on, I want to address something. We've been talking about nations and companies racing into space, but there are critics who argue this whole enterprise is problematic, that we're exporting extractive capitalism to the cosmos.
That's a legitimate perspective. Some argue that space resources should remain untouched, that we shouldn't replicate on other worlds the environmental destruction we've caused on Earth. There is also the existential argument. Becoming a multiplanetary species requires space resources to build off-world infrastructure.
What about public opinion?
Interestingly, a 2022 study found that the public is largely in favor of asteroid mining, more so than deep-sea mining, Antarctic mining, or wilderness mining on Earth. People seem to view asteroids as acceptable targets in a way that protected terrestrial environments aren't.
Nobody's protesting for asteroid rights.
Not yet, though I wouldn't rule it out eventually.
All right, we need to tackle the economic paradox, why mining Psyche might actually make us all poorer.
We've spent nearly over 1 hour talking about how to get to Psyche, what's stopping us, and who's racing whom. But there's a fundamental question we've been dancing around. Even if we could mine Psyche, would it actually make anyone rich?
This is where the 10,000 quadrillion number reveals its absurdity. That valuation is based on current market prices for iron, nickel, platinum, and other metals. But those prices exist because supply is limited.
And flooding the market with asteroid metal would
crash prices completely. If you suddenly introduce quantities of platinum that exceed all the platinum ever mined on Earth by orders of magnitude, platinum stops being precious. It becomes common.
So the more you mine, the less each unit is worth.
Exactly. Economists call this the asteroid mining paradox, or sometimes the resource curse for space. The theoretical value assumes you can sell at today's prices, but the act of selling destroys those prices.
Give me a concrete example.
Let's take platinum. Global platinum production is about 180 to 200 metric tons per year. If a single asteroid mining mission brought back, say, 10,000 tons of platinum, which would be a tiny fraction of what Psyche contains, you've introduced 50 years of normal supply in one shot.
The price would crater.
It would collapse. And here's the thing. Platinum isn't just jewelry and investment, it's industrial. Catalytic converters, electronics, medical devices. Those industries would benefit from cheaper platinum, but the miners would never recover their costs.
So the first mover gets destroyed?
Potentially, unless they control the release of material very carefully, dribbling it out to match demand rather than dumping it all at once. But that requires managing supply for decades, essentially becoming a monopolist.
Which has its own problems.
Legal, political, and practical problems, yes. And if multiple companies are mining, coordinating supply restriction becomes a cartel situation with all the antitrust issues that entails.
Lindy Elkins-Tanton, who calculated the original 10,000 quadrillion figure, she acknowledges this, right?
Absolutely. She's been very clear that the number is essentially meaningless for practical purposes. There's no technology to mine Psyche, no way to bring back significant material, and no market that could absorb it without collapsing.
So why does the number keep getting quoted?
Because it's attention-grabbing. 10,000 quadrillion space rock makes headlines in ways that scientifically interesting but economically inaccessible asteroid doesn't. The media and public latched onto the valuation because it's dramatic.
Is there any scenario where asteroid mining is economically viable?
Yes, several. First, the in-space utilization model we discussed earlier. If you're producing rocket propellant or construction materials for use in space, you're not competing with terrestrial markets. You're providing something that has no Earth-based alternative.
So space gas stations work economically even if shipping platinum doesn't.
Right. The value proposition is different. Instead of cheaper than mining on Earth, it's the only option for operations beyond Earth.
What else?
Second, focusing on truly rare materials where even small quantities have enormous value. Some asteroids may contain exotic isotopes or materials that are genuinely scarce throughout the solar system, not just on Earth.
Any examples?
Helium-3 from the Moon is often cited. It's rare on Earth, but potentially useful for fusion energy. There's a Seattle startup called Interloon, specifically focused on lunar helium-3 extraction.
Third option?
Third, redefining the business model. Maybe asteroid mining companies don't sell raw materials, they sell manufacturing capability. Build products in space, where zero gravity and vacuum enable manufacturing processes impossible on Earth.
Like what?
Perfect ball bearings, fiber optic cables without impurities, organs printed without the distortions caused by gravity. There's already interest in space manufacturing for high-value products.
So asteroid resources become inputs for space factories rather than exports to Earth.
Exactly. The resources never return to Earth. They become infrastructure for an expanding space economy.
That sounds like a generational project.
It is. We're talking about building an entire economic ecosystem in space, not a single profitable mine. That's why serious space mining advocates talk about decades of development, not quick returns.
What about the transition period? How do space mining companies survive while waiting for the space economy to mature?
That's the billion-dollar question, literally. The current approach, developing Earth-based revenue streams while pursuing space ambitions, is one answer. Government contracts are another, and some companies are essentially betting on being early enough to establish monopoly positions.
First mover advantage?
In theory, though as we discussed, first movers in space mining haven't historically done well. Planetary resources and deep space industries both failed despite early leads.
Is Psyche specifically ever a mining target, even in the long term?
Probably not for centuries, if ever. The asteroid belt is much harder to reach than near-Earth asteroids. Even if we solve all the technology challenges, economics would favor closer targets.
So Psyche remains science, not treasure.
For any foreseeable future, yes. The 10,000 quadrillion is theoretical value of resources we have no practical way to access, situated in a location that makes retrieval economically unfeasible even with advanced technology.
That's slightly depressing.
Or liberating, depending on your perspective. Psyche's value isn't diminished by being scientific rather than economically important. Understanding planetary formation, core structure, and early solar system conditions, that's enormously valuable to human knowledge.
Just not to human bank accounts.
Not directly, no. But scientific knowledge enables technologies we can't predict. Who knows what understanding metal asteroid composition might enable 50 years from now?
Let's talk about the near-term economics. Astroforge, the leading asteroid mining company, are they economically viable?
They've raised $55 million, which sounds like a lot, but is actually modest for aerospace ventures. Their model depends on dramatically reducing mission costs. They're aiming for under $10 million per mission.
Is that achievable?
It's ambitious. SpaceX has reduced launch costs significantly, which helps, but the spacecraft themselves, the refining equipment, the return vehicles, all remain expensive. Whether they can hit those targets with functional systems remains to be demonstrated.
What's their path to profitability?
First, demonstrate they can fly by an asteroid and characterize it. Then demonstrate they can land on one and collect material. Then demonstrate they can process and return it. Each step builds credibility and potentially opens new funding.
But they're not profitable yet.
No. Asteroid mining companies are profitable. They're all pre-revenue, investment-funded ventures betting on a future market that doesn't yet exist.
Venture capital is patient, but not infinitely patient.
Exactly, which is why timeline matters. If commercial-scale mining really is 30 years away, as some experts suggest, that's multiple investment cycles without return. Not many investors sign up for that.
Are there any wild cards that could accelerate this?
Several. Major breakthrough in propulsion technology, say fusion rockets, could dramatically change the equation. Massive government investment analogous to the Apollo program could compress timelines. Discovery of something uniquely valuable on a near-Earth asteroid could change incentive structures.
Or just gradual progress?
That's the most likely scenario. Steady improvement in launch costs, spacecraft capability, and autonomous operations, eventually making mining economically feasible. No single breakthrough, just decades of incremental advancement.
Like how aviation developed.
Good analogy. The Wright brothers flew in 1903. Regular commercial air travel didn't emerge until the 1930s. Mass aviation took until the 1960s jet age. Space mining might follow a similar pattern: first flight, proof of concept, early adoption, and eventually, ordinary commerce.
Except we're still at the Wright brothers stage.
Maybe slightly past it. We've landed on asteroids, returned samples, we're about to study a metal-rich one up close. We're perhaps at the 1910 stage, showing it's possible, not yet showing it's practical.
All right, Elena, we've covered a lot of ground, or a lot of space, I should say. Let's wrap up by looking forward. What should people be watching for in the next few years?
Near term, watch the Psyche mission's Mars Gravity Assist in May 2026. That's the next major milestone before arrival at the asteroid in 2029. Watch Astroforge's Vestry mission, which aims to land on a metallic asteroid. If successful, it would be a major milestone for commercial asteroid mining.
What about national programs?
China's Tianwen-2 mission returning asteroid samples in 2027 will be significant. The ESA's Hera mission, arriving at Didymos in November 2026, will advance both science and planetary defense. And NASA's Artemis program, Artemis 2, is scheduled for 2026 as the first crewed mission back toward the moon in over 50 years.
What are you personally most excited about?
Honestly, the first high-resolution images of Psyche's surface. We've never seen a metal-rich asteroid up close. Everything we know is from Earth-based observations and inferences. Seeing actual terrain, craters, metal exposures, that's going to be spectacular.
When do we expect those images?
The approach phase begins in May 2029, so we'll start getting increasingly detailed views through the summer of 2029, with the science campaign beginning in August. Mark your calendars for summer 2029.
What about asteroid mining specifically?
Watch whether Astroforge's Vestry mission succeeds. If they can land on an asteroid and take measurements, it proves a capability that's essential for future mining. If Carmen Plus's 2027 mission demonstrates water extraction, that validates the in-space utilization model.
What should audiences take away from our conversation today?
3 things. First, the 10,000 quadrillion number is fascinating, but essentially fictional. Don't expect anyone to get rich from Psyche. Second, the real value of space resources is enabling future space activity, not replacing terrestrial mining. Third, we're at the very beginning of the story. The technology, economics, and law are all embryonic. What matters now is scientific foundation building.
And if you had to bet on when we'll see actual asteroid mining at commercial scale?
I'd put the over-under at 2055. Initial demonstrations this decade, early operations in the 2030s to 2040s, and something resembling a mature industry by mid-century. But space has a way of surprising us, both faster and slower than predictions.
Any final thoughts?
Just that Psyche represents something beautiful about human ambition. We know there's a metal world out there, impossibly valuable, tantalizingly close on cosmic scales, but
utterly out of reach with current technology. And instead of ignoring it, we're sending a spacecraft to study it, building the knowledge that future generations might use to finally reach it.
Planting seeds for a harvest we won't see.
Exactly. That's what exploration has always been. The people who studied the ocean currents never built the ships that crossed them. The scientists who understood orbital mechanics never walked on the moon. We're adding to that chain of knowledge.
That's a beautiful place to end. Elena, thank you for spending time taking us through the Psyche asteroid, the 10,000 quadrillion we can't touch, and the future of space resources.
Thanks for having me, Marcus. This has been a blast. And if you're still in school or early career, consider that by the time you're mid-career, asteroid mining might actually be a job. The industry will need geologists, engineers, roboticists, lawyers, economists. This is a field that's going to need everyone.
Space needs people. I like that message. All right, that's our show. I'm Marcus Chen.
And I'm Dr. Elena Vasquez.
Until next time, keep looking up, even if what's up there is temporarily out of reach.